So, welcome to the session on planar flows as part of the NPTEL MOOC on transport phenomena in materials. By planar flow, we mean flow field where the velocity vector has only two components, and we can also call them as 2D flows. So, a quick recap of the continuity equation which we derived and used in the previous session. So, we are writing here the continuity equation for an incompressible fluid, and if you take the general three dimensional flow field u, which is given by the vector u here, then it has three components u1, u2, u3, and therefore, the continuity equation or the mass balance for an incompressible fluid will become that the rate of dilation, which is given by the symbol delta, is equal to grad dot u is equal to 0, and we have got this equation. Now, this equation can also be written in other coordinate systems, and we have done that earlier and introduced. So, in cylindrical coordinate system, the velocity will have the radial component, the theta component and the z component, and the continuity equation would look like this. And in the spherical coordinate system, you would have the radial velocity, the theta component and the phi component azimuthal, and then the continuity equation would look like this. And the application of continuity equation can be done in various ways. So, we have basically a possibility to validate the velocity field as being valid or not, which means that is the velocity field allowing the mass conservation to be possible, and if it passes the test, then it means that it is a valid velocity field which we can use. And we can also use this continuity equation to determine unknown components from a velocity field. So, in this case, for example, if you have two components u1 and u2 available, and we want to find out what is the u3 component, then readily we can plug in u1 and u2, integrate the expression with respect to x3, and then we have got the u3 component made available. And in the case of 2D flows, for example, we can also reduce the number of unknowns from two components of the velocity to one unknown using the continuity equation, because it can be treated as an additional constraint, and that is exactly what we are going to do in this session. So, in this session we are also going to be introduced to some new terminology, stream function psi, potential phi and vorticity omega. We are going to define these things as a part of this session, so that we can also use them to describe 2D flow fields. We will also be getting used to the terminology used to describe the flow field in 2D when we want to call something as a uniform flow or a source flow, sink flow or a doublet flow, vortex, etc. Generally, we can use combinations of these to determine how the flow would be called in any general situation. So, we want to find out what is the expression that can be used for each of these elementary planar flow fields. So, we are now going to reduce the number of unknowns in a 2D field. So, you have basically two components of a velocity field. Here we are having them as Vx and Vy as the components in 2D. So, which means that we now have the continuity equation having only two terms, and that is written here, and we can use this equation to reduce the number of unknowns from 2 to 1. So, the way we do it is as follows: we will define a function psi in such a way that this is how the velocity components are defined. So, you define psi in such a way that the velocity components are given by the differentiation of psi with respect to x and y as here. So, what happens when we do that is, when we then plug in to the continuity equation, then you could see that the first term would become dou by dou x, and then the Vx actually is dou psi by dou y, and then the second term is dou by dou y, and Vy is actually minus of dou psi by dou x, and this implies that it is dou square psi by dou x dou y, and here is a minus, and dou square psi by dou y dou x is equal to 0, but this is true for any well behaved function psi. So, if psi is a well behaved function, then this is always true, which means that if we can actually come up with a function psi which is well behaved, then we can take its derivative with respect to x and y, and then call those two expressions as velocity components, because they would readily satisfy the continuity equation. So, because of this utility, we actually would like to give a name for this function, and we call it as stream function. Okay, so the reason why it is called as a stream function will be evident in a moment, but at this moment we would just call psi as a function that allows us to generate the velocity components. Okay, so we could have defined, for example, these expressions we could have defined with the minus sign either for the Vx component or Vy component. It could be both options are possible, and the continuity equation would satisfy either way. But there is a convention by which we define, and that convention is what is being introduced. The convention is as follows: the derivative of psi, if you take along one direction, then 90 degrees away in clockwise is the velocity component being given. So, which means that if you look at this first expression, you can see that dou psi by dou y is being taken in this direction, and then 90 degrees away is this direction, which is x, which means that is what is being given as a component. And you can see the second expression, again the same thing is valid. You are differentiating with respect to the x, which means that you are differentiating in this direction, and then 90 degrees away will be this direction, which is actually the minus y direction, and so this will be giving velocity in the minus y direction, and that is why there is a minus symbol here. So, this is the convention that is used, so that in any other coordinate system, if you want to define the velocity components, and if you follow this convention, then the sense of psi that we use will be the same in all the coordinate systems. So, for example, if you take the cylindrical coordinate system, the r vector is shown here. So, which means that when we differentiate with respect to r, then 90 degrees away will be minus theta direction, and that is why you have a minus sign here, and then if you differentiate along theta direction, then 90 degrees away is r direction, and therefore we got Vr there. So, the convention is being used in all coordinate systems the same way, and the convention is basically differentiation of psi in a direction gives velocity component 90 degrees clockwise from that direction. Okay. Now, what is the meaning of this function, stream function? We have mentioned that it is useful. It will definitely reduce the number of components from 2 to 1, but then does it have any sense in this what we can actually call it as? So, we have that being defined here. So, consider a small volume element, and remember that we are using it for 2D flows. So, the area element in 2D will become a line element. So, we want to consider a line element as follows. Okay. So, I take a line element like this. Okay. So, this small line element between O to P will then be given in terms of its components dx and dy, and in two perpendicular directions. Now, in the vertical direction, if you have unit depth, which means that we are talking about flow through this plane. Okay. So, we are talking about the flow through this plane, and you could see that the flow through that plane can be thought of as flow through the two planes that we are indicating here. One is through this and another is through this. Okay. So, you can actually split the components in this manner, and the convention that is used to tell whether psi is actually positive or negative is as follows. About P, the flow we are giving is actually anti-clockwise. So, I have given this direction here. So, about P. So, which means that if you are taking the value with reference as the O point, then phi p minus phi o is given as the flow through the line segment in the anti-clockwise direction. And then now, why are we saying that it is actually the volume flow of fluid through that segment? That will be evident like this. So, you see that the psi is actually a well behaved function. So, you could write the exact differential of psi in this manner. So, it is now a function of x and y. So, you could write it like that. And when you write it like this, and you can already see that the two differentials can be expanded, and you now have this expression. So, which means that because this is an exact differential, so you could actually say that psi p minus psi o is nothing but integration from O to P d psi. Okay. Now, d psi is actually already available to us. So, that is what we plug in here, and that is what we have written here. Okay. Now, you can see that term by term, what does it mean? If you take the first term u dy is basically velocity in the u direction through the dy element. Okay. So, this is the dy element, and the velocity is in x direction. Okay. So, which means that the first term corresponds to flow through this area element. Okay. Similarly, the second term. So, you could see that the distance from O to P is actually minus dx. So, which means that the second term is v velocity through this plane, okay. Okay, and which means that together when we sum them up in this manner, it would mean that we are talking about the flow through that plane, which is nothing but this element with a unit depth in the z direction. So, we can see that the meaning of this quantity psi is nothing but in relation with respect to the psi value at another location, reference value at a location O, it gives you the volume of fluid going through the area that is formed by the line segment OP and the unit depth in the z direction. And if you forget the z direction for a moment, it means that the volume flow across a line segment PO. Okay, so, that is what is the meaning of psi here. It also means that when you have the psi field plotted as contours, then the distance between the two contours will actually give you the measure of the fluid flow in that particular direction. Okay. So, we could actually, now that we have this function psi, we could actually define it for other coordinate systems. So, we are defining it, for example, here cylindrical coordinate system where r and theta are the two directions, and we assume that z direction there is nothing happening, there is no velocity in the z direction, and therefore, we can write the continuity equation with only two terms, and that is what is done here. And then we define the psi in the same manner with the same convention as we have done earlier, and we could see that when we substitute these, then the continuity equation is quite satisfied. So, you could already see that the r gets cancelled and you have got each term giving a dou square V r dou square psi by dou r dou theta with plus sign in the first term and minus sign in the second term. So, therefore, automatically it is satisfied. So, if you want to generate the velocity components in a cylindrical coordinate system, then we come up with any function psi, which is a function of r and theta, and then take the differentiations like this, and then they will become the component of velocities along r and theta directions, because this already takes care of the continuity equation to be valid. So, we could also define the stream function in a cylindrical coordinate system in another manner. So, in the first case, for example, we are taking it in the form of a r theta, which means that it is within the plane, okay. And here we are actually taking for axisymmetric flows, because the theta variation is now being dropped. Okay. So, this is also 2D flow, and we could then see that the terms that are remaining in the continuity equation are a different pair, and you could also define the stream function in the cylindrical coordinate system for axisymmetric flow in this manner, and we could readily see that when we substitute, we will see that the continuity equation is satisfied. So, this way we can actually define the stream function for 2D flows in a cylindrical coordinate system in two different manner. Okay. And we could also do that in a spherical coordinate system, and the difference between spherical and cylindrical will be evident here. So, watch out the power of r. So, you could see that here it is 1 by r and here it is 1 by r square. So, even if you did not label the expressions correctly, sometimes we can actually detect it by looking at these terms carefully. And the continuity equation in a spherical coordinate system where the phi dependence is lost, then we can actually see it as a 2D flow, and the continuity equation is given with the two terms. So, which means that the stream function in a spherical coordinate system can also be defined in this manner, and these two are the expressions that we use to generate the fluid flow components in r and theta directions in a spherical coordinate system. Okay. So, now that we have defined it, we have also other quantities that we need to make ourselves familiar. So, we introduce a quantity called vorticity omega. So, vorticity actually is nothing but the curl of the velocity vector u. The reason why we say that this quantity is important will be evident in a moment. Okay. So, we have this curl, and we already saw that this is applicable, okay, and we now want to give a name for this quantity. Okay. So, this is applicable because of continuity equation, and we want to give a name for this, because when that is 0, we want to define it with another name. Okay. So, if this is 0, that if vorticity is 0, then we want to give a name for that kind of a planar flow, and we call it as a irrotational flow. Okay. So, the way this omega is defined is such that we have a sense of circulation of the flow. Okay. So, the circulation of flow is defined in this manner. Capital gamma is a line integral around a closed loop given by this expression u cross ds, where the ds is the length element along the loop. Okay. So, you are integrating along a closed loop, and for every segment ds we want to now do this integral, and we could then already see that using the Stokes theorem in 2D we can actually convert the cross product into the dot product, and we can already see that the circulation is given by omega itself. So, we can say that the vorticity and circulation, the sense of how the fluid is actually going around, is actually embedded in the definition of vorticity because of this expression that we have written here. And in the case that the omega is 0, then we would like to call that flow as irrotational flow. So, the reason why we have actually come up with this particular type of flow is because it allows us to define another quantity which we call as velocity potential, so that we can actually generate the velocity components for a very specific 2D flow situations. So, we call that as basically velocity potential in the following manner. So, we saw that if it is irrotational, okay, if the flow, okay, is irrotational, okay, which means that we say that this is 0 or the curl of u is 0, then we know from the vector identities that if this vector happens to be actually a gradient of a scalar function, then it will be always true, which means that if we were to now think of this as related to some kind of a gradient of a function phi, then this will always be true for any well behaved function phi, and we want to define with a minus sign. Okay, that is because generally it is felt that potential is one where its gradient should lead to the flow. So, if you want to have that, then the down the potential gradient is the flow taking place. It is true for many other phenomena as well. For example, temperature gradient, down the temperature gradient is where the heat is actually flowing, and so on. So, in that similar way, if you want to define, then we will put that minus sign there. So, which means that we have one more way by which we can generate the velocity components, that is by using the velocity potential. So, you could see that the way velocity potential is used to create the velocity components is given by this expression. You could see that this is different from the stream function expressions. You could see that the indices are matching here, and in the case of a stream function they will be opposite. Okay, so, that is how we can just recognize these expressions very different, and we can now go ahead and see what are the kind of functions phi which we can come up with, and then plot the velocity vectors for all those functions and see how those flows look like. And then by giving names to such flows, then we can actually describe in any arbitrary situation how the flow is actually happening. Okay. Now, the way we go about creating these potentials is as follows. So, if we have created a function phi which is like this, we already know that it satisfies the continuity equation. We see that then this must be true, which means that any function phi which satisfies the Laplacian Laplace's equation must be valid for us. Okay. So, which means that we now look for functions of phi such that this is valid. Okay. Then we automatically know that the continuity equation is valid, and we also see that it is going to give us the velocity component. So, this is how we go about generating them. Technically, the stream function gives us flow components in 2D, but the velocity potential has no such restriction. It can give us velocity components in 3D as well. So, it is a little more generic concept than stream function. Okay. So, the potential flows are basically flows where the flow is irrotational, and the flow is also coming with the components from the velocity potential function. Okay. So, such flows are categorized separately as potential flows, and we can then see how they can be arrived at. So, we could also see those potential flows in other coordinate systems like cylindrical coordinate system, and we can see that we could define the components in this manner. The r theta components of the flow for a potential flow can be defined in this manner, and we know that when we substitute into the continuity equation, then it will be satisfied. Okay. So, what is the relationship between these two things that we have just now introduced? We have introduced psi, which is the stream function. We have also introduced velocity potential phi. So, how are these two related. So, we know that the psi has a meaning that difference in the values of the contours of psi represent the volume flow between those two locations, and the velocity vector at any point is tangential to the contour of psi through that point. So, which means that if we draw contours of psi in any domain, for example, if it were to look like that, okay, so psi 1 and psi 2. Okay. Now, what it implies is that when we take a tangential vector, then this vector is actually also going to give us the velocity components at that particular location. Okay. So, that is how the sense of flow is captured by the contours of psi. Okay. That is one utility of the stream function. And we also know that if you look at the components, that the contours of phi will be normal to that of psi. So, this we will also practice with one or two examples shortly, and one can also take it as a homework to prove the same. The idea is basically take the exact differential of phi and exact differential of psi, and then inspect the terms, and then that will be evident to you. Okay. So, we have some examples now. So, we are going to introduce elementary planar flows here. So, we have those names coming up, and those names and those flow patterns, that is a kind of relationship that we want to now use to describe flow in any arbitrary situation. So, uniform flow, as a word immediately implies, it means that the velocity is constant and in only one direction, and you could actually see that the uniform flow can be described in this manner. You could have the phi or psi which is ay or minus ax. So, which means that it is a potential flow, and we could actually generate them either through the stream function or through the velocity potential, and the velocity itself is given in this manner here. So, in all these examples in the next several minutes, we are going to give the velocity components and also from where they are generated. So, you should use the expressions that are given in this session on how to generate the velocity components from stream function as well as the velocity potential, and verify that all these expressions are valid. Okay. So, when we take this field and then plot it in a software, for example, this particular plot is made using Mathematica. So, you can plot and see how the flow field would look like. So, obviously, this can be extended to any other direction. So, you simply have to change these x and y to be y and x respectively, and you have the uniform flow in another direction that is coming up. Okay. So, the stagnation flow is basically something that we have discussed earlier, namely flow near a corner. So, if you have a corner and how the flow would look like near the corner is described by a type of flow that is called as a stagnation flow. And the stagnation flow has the phi function given here, and you could also see here that the stream function and the velocity potential are given here. And when you plot the contours, you could already make out. So, 2xy you see that these must be hyperbolae, and you can already see that the stagnation flow will give you hyperbolae. Okay. So, just a moment to recollect what we discussed earlier about the contours of stream function and velocity potential being normal to each other. So, let us just look at this. What would be the contour of stream function? It will be at different values of y, which means that those contours are going to look like that. Okay. So, these are the contours of psi in this particular situation, and we can see that the contours of phi will be different values of x. So, those would be looking like that. Okay. These are the okay. So, as you can see that at every point where they are intersecting, the contour of psi and contour of phi are normal to each other. So, this can be validated for all the flow fields when we go ahead. Okay. So, that is what I was telling earlier, and here you could see that the contours of psi will be given by hyperbolae, and then the contours of phi should be normal to them wherever they are intersecting, and the velocity components are given by the components that are here minus 2x and 2y. So, the flow field near a corner can be described by stagnation flow. Sink flow is a situation where you have got a singularity, a location at the center. Here in this case it is 0 0 location, where the flow is actually converging, and you have a problem there actually, but you could actually imagine that this is a flow field where in a tank there is a small hole at the center, and then the liquid is going through that to the bottom. So, that kind of a flow field can be described using sink flow, and the stream functions and velocity potentials for sink flow are given here. You can see that the logarithm r is what is giving you the velocity potential, and if you take differential with respect to r is 1 by r, and you can immediately see that the velocity is unidirectional along r direction as 1 by r. So, in the case of cylindrical coordinate system, we already know that in a single component velocity, as you go away from the origin, the strength of the flow field has to come down as 1 by r, and that is already used here. So, the insight that we have from continuity equation can be readily applied here. So, the way we plotted here, it is not evident, but the magnitude of these vectors should die down as 1 by r when you go from center to the distance away from center. So, the source flow is the exact opposite of sink flow. Here basically the directions of the arrows are reversed, and you could see that it can be given by the function that is just with a minus sign. Okay, so, you could also see from here the velocity components are just plus of q by 2 r. So, the quantity q in both the sink flow and the source flow basically indicate the volume flow rate per unit depth in the z direction, and that can be used to calibrate the velocity components in the r direction. Okay, so, there is another flow field, elementary flow field called doublet, and doublet is described by stream function and velocity potential that are given here. So, you have got a sin theta and cos theta there, and now here actually it is not really a unidirectional flow. It has two directions, both r and theta direction components are available here, and when we plot them you can see that the flow looks like here. We can imagine that the flow is basically in this manner, okay, and you have got one rotation this way and another rotation that way. Okay. So, the doublet flow can be coupled with other flows to generate complicated real life flow situations. The idea why we are introducing elementary planar flows is because in situations where we need to have some idea of how the flow field would look like, we can mix and match these things and calibrate and arrive at a velocity flow field without even solving any equation. So, that is one of the applications of using elementary flow fields. Okay. The last one is vortex flow. So, vortex flow, as the name indicates, should have a rotatory motion of the liquid. So, you can see that vortex flow would look like that. Okay. So, where the liquid is going around, and you have basically that as only the theta component being present, r component is not there. Okay. Now, you can already see that the magnitude of the velocity should go down as 1 by r for cylindrical coordinate system, and that is also satisfied. Okay. So, you could plot the contours of psi, and you could see that they go in circles, concentric circles, to give the sense of flow that is going around the origin. Okay. Now, the application of elementary flow fields is to describe situations that are close to real life situation, and be able to combine the elementary flow fields to arrive at a flow field that looks quite realistic. So, you could already see that in this case flow past a half body. So, where is that half body? You could think that the half body is like that. So, you have, so how does the flow happen around that? So, that is what actually is now being shown. Okay. So, you can see that a flow past a half body can be described using a source flow and a uniform flow together. Okay. So, you can take those two functions, simply add them up and then plot, and then you get this kind of a flow field. And when you add, you can also have calibration factors for both these terms, so that you can make the strength of these velocity gradients different as the requirement comes up. And if you take a source or a sink and then add it to a vortex, then you would have a spiral flow. So, you could see that here there is a spiral flow that is coming up, and the direction of spiral can be reversed if you change from source to sink that is being added to a vortex. So, doublet and uniform flow can then be combined to see how the flow would look like when it is going past a cylinder. So, the cylinder is here. Okay. So, the velocity past a cylinder would require it to go up and down like this, and we can already see that the combination of these two functions already gives us that kind of a sense of the flow. So, without solving any equation, we can come up with the velocity field description for flow past a cylinder directly in this manner. So, that is one of the uses of elementary planar flows. So, if you then have one more element that is being added, a vortex being added to doublet and uniform, then it would help us to see that it is for flow field around a cylinder which is having a rotation. So, these two are very similar situations, only thing is on the left hand side we have got the cylinder stationary and the right hand side it is rotating, and the flow field around such cylindrical bodies can be given by a combination of elementary planar flows. So, here are some real life situations encountered in metallurgical industry where these elementary planar flows can be used. For example, here this is what we call as a ladle and this is what is called as a tun dish. Okay, and the process that we are seeing here is a continuous casting process, and this is the caster. Okay. So, liquid is coming into the caster and then it is becoming solid. So, by the time it comes out everything is red here, which means it is fully solid, the yellow is the liquid metal. So, if you now see the way the liquid metal is coming out of the ladle, you could see that the ladle has a small hole at the bottom and through which the liquid is coming down. So, which means that you could describe the flow of the liquid metal at the bottom of the ladle using elementary planar flow field, which is basically a sink flow. So, a sink flow is adequate to describe the flow in this region. You could also describe in the case where the flow is not very turbulent, then you could actually see that in this plane you could use source flow to see how the flow is happening. And if you have obstacles that are placed in the tun dish so that the inclusions that are coming, the draws and inclusions that are coming with the melt do not enter the caster, then if there is a cylindrical obstacle that is placed, then the flow around that obstacle can then be also described using elementary planar flow fields that we have discussed just now. Okay. And you could also see that tapping the liquid metal from a ladle also can be described using sink flow. So, you could see that the ladles have a small hole at the bottom through which the liquid is being drawn out, and that can be described using sink flow. So, like this in a metallurgical industry some of the flow fields can be directly described without having to solve any equations using elementary planar flow fields. So, here is another metallurgical situation where we have a welding setup. Okay. So, here we have a welding torch, a plate that is being welded, and the torch is going to move from left side to the right hand side, and the liquid metal is at the center, and to protect the liquid metal from getting oxidized from the ambient air, we have a gas shroud. So, the gas is actually going through these and it is going to have a shroud around the liquid metal to protect. So, the way the gas is actually coming out of this nozzle can also be described using a source flow. So, in situations where we are unable to solve equations to arrive at the flow field as a function of x and y distances in situations like this, if you want some approximation, then you could use elementary planar flow fields to make those approximations, and then go ahead and make some estimates as a very first measure of how this flow is happening. Okay. So, with this we close this session on elementary planar flow fields and the 2D flow, and we will have some exercises that are possible to check the various components, whether we are able to express the velocity components using those two functions that we have come across, the stream function and the velocity potential. So, we will have some practice assignments that will be put up in the course website for that. The plots are made using Mathematica. So, the Mathematica notebook that is used to make all those plots are is also going to be uploaded into the course website. So, you could use it to make some changes and play with those flow fields, and then gain an insight into how those functions will determine those flow fields.